Hello, everyone. Welcome to our third lecture of GPU computing. Today, we're going to be talking about multidimensional grids and data. So a lot of applications out there, a lot of data out there is multidimensional. And when we're processing this kind of data, when we're implementing these kinds of workloads, it's convenient to have multidimensional grids, and CUDA actually supports that. So we'll be seeing how to do that in today's class. So last time we spoke about data parallel programming. We had an introduction to data parallel programming, and we used the CUDA programming model to demonstrate that. And our example that we had throughout the class was vector addition. We said there's two types of parallelism. There's task parallelism and data parallelism. Task parallelism is where we do different kinds of tasks in parallel, and these tasks could be on the same or different data. And we said that with task parallelism, usually you can unleash a modest amount of parallelism because there's usually a small number of different kinds of tasks in a program that can run in parallel. Whereas with data parallelism, we perform the same operation on different parts of the data. And data parallelism gives us higher potential for the amount of parallelism that we can get, because once your data set gets larger, you get more and more data parallelism in your application without having to write new code as you would for different kinds of tasks. So the vector addition example that we looked at involved taking two vectors and adding them to get an output vector. And we saw how to do that sequentially, and then we said, why don't we try and offload this to run on the GPU? And that typically when you want to run on the GPU has a separate memory from the CPU. And therefore, when we want to offload some computation from the CPU to the GPU, we have to allocate memory on the GPU, copy data from the CPU to the GPU. Then we run on the GPU by accessing the data in the GPU's memory, and then we copy data back from the GPU's memory to the CPU memory, and then we deallocate the data. And we saw the different interfaces that CUDA gives us to do this. We saw CUDA malloc for allocating, CUDA memcopy for copying to the GPU and back from the GPU, and CUDA free for deallocating from the GPU. And the remaining part was to run many threads on the GPU to perform the operation. And to do that, we saw how CUDA grids are organized into blocks. So we said that a grid is an array of threads, but these threads are organized into blocks. And for different threads in a grid to distinguish themselves from each other, they have access to these keywords that are available in CUDA, particularly the grid dimension, which tells us the number of blocks in the grid, the block index, which tells us the index of the block with respect to other blocks in the grid. We have the block dimension that tells us the number of threads in a block. And finally, we have the thread index that tells us the index of the thread with respect to other threads in the same block. And we said that if we wanted to find the global index of the thread, in other words, if we want to find how many threads a thread is from the very beginning of the grid, then what we can do is we can take the block index, multiply it by the block dimension, which is the number of threads in the block. That gives us the number of threads to the beginning of the block. And then we add the thread index, and that gives us the global index of the thread. And this was important because the way we parallelize vector addition is by assigning a thread to each element in our array to load the two elements, do an addition, and then store the result. And the way we did this is by every thread executing int I equals blockdim.x times blockIndex.x plus threadIndex.x, and then we do z of I, which is the output vector, equals x of I plus y of I. So by doing this, each one of these threads executes the same code, but each one of these threads has a different block index and a different thread index, and therefore each thread gets a different I, and each thread will load two different elements, add them, and store them for a different output. We said that for compilation, a CUDA code is compiled using the NVIDIA CUDA compiler, NVCC, which separates out the host code, the CPU code to run on the CPU, and the GPU code to run on the GPU, and it takes care of that separation for us. So we can write CPU code and GPU code in the same file, and the CUDA compiler takes care of separating those, calling the host compiler to compile to the CPU, and then when we run the PTX code generated by the CUDA compiler will invoke a just-in-time compiler that will compile to the device assembly so that that code can run on the GPU. So this was a quick overview of what we covered last time. Any questions about this? Everything clear to everyone? Okay, so then today what we're going to do is we're going to continue with data parallelism, but we're going to look at how to create multi-dimensional grids. We're going to look at how to store and access multi-dimensional data, and we're going to have three running examples throughout today's lecture. The first one is converting a colored image represented with RGB to a grayscale image. The second one is blurring an image, and then the third one is matrix-matrix multiplication. Okay, so let's start with RGB to grayscale. So RGB to gray, what this computation does is it takes a colored image, and in a colored image, an image is basically an array of pixels. So every pixel is represented using three components: a red component, a green component, and a blue component. And what we'd like to do is we would like to take this colored image and convert it into a grayscale image, where every pixel is just one value that represents an intensity, so a range between black and white. So if we want to process this in parallel, what is an obvious way of using data parallelism to process in parallel? What do you suggest? How do you suggest we can parallelize this?
Give each thread a pixel.
Right, exactly. So what we can do is we can give each thread a pixel. So the parallelization approach, the straightforward one, is to assign one thread to convert each pixel in the image. Now the image is a multi-dimensional array, right? It has a width and it has a height. And because the image is a multi-dimensional array, it's convenient for us to be able to have our threads also have multi-dimensional indices. And it turns out that CUDA actually supports multi-dimensional grids. And CUDA supports two-dimensional grids, three-dimensional grids, in addition to the one-dimensional grids that we saw last class. And the nice thing about this support is that it simplifies processing multi-dimensional data for us. If it didn't support this, that would have been okay. We could just have converted our one-dimensional index into a two-dimensional index. But it does, and that makes processing very convenient. So if we have an image like this is an image of a tree. The way that we can parallelize this is we can assign a thread to each pixel in this image, and our grid of threads is going to be a two-dimensional grid, where the grid has you can think of each of these blue squares as being a thread block. So here the grid is going to have 2 by 2 thread blocks, and each thread block is itself going to be a two-dimensional array of threads. So here each block has 4 by 4 threads. In practice, of course, we have much more threads in a block and much more blocks in a grid. But here, just to simplify the illustration, we're having a small number, so 2 by 2 and then 4 by 4. Okay. Okay. So what we want to do is we want to be able to launch a multi-dimensional grid, and let's see how to do that. So somebody is asking, isn't it better if we gave each color in each pixel one thread? Well, if we gave each color in each pixel one thread, what that means is we have a thread for R and a thread for G and a thread for B. But what we want to do is we want to add R, G, and B and find some kind of a weighted average between them. And that is a sequential operation. So these three threads would have to be communicating with each other to do the addition. And with this little amount of work, it's probably not worth the communication overhead between the threads. If I was adding 1,024 different channels in my image, so if I had 1,024 of these, R or G or B, if there was 1,024 of those, then maybe you would have multiple threads per pixel. But in this case, we only have 3 values per pixel, so it's not really worth dividing it further than one thread per pixel. Okay, so let's see how we can create a multi-dimensional grid. So I'm going to switch now to CUDA code. I have this CUDA program written that does an RGB to gray conversion. I've already written the code to do the allocation. Written the code to do the allocation over here. This is doing CUDA malloc for the red component and the green component, an array that has the red parts of the pixels, an array with the green part of the pixel, an array with the blue part of the pixel. And then I have allocated an output array with the gray part of the pixel. I've copied the input arrays, so the red, the green, and the blue. I've copied those to the GPU. And then we have to somehow call the kernel, and then we are going to copy it back, and we're going to free the result. Okay, so you guys already know how to do all of this from last time, but what we want to look at today is how can we call a kernel that has multiple dimensions. Okay, how can we call a kernel and configure it so that the thread block has multiple dimensions? The kernel that we're going to be calling, we're going to implement later on, it's called RGB to gray kernel. Okay, and it takes red, green, blue arrays and has a gray array for the output, and it has an integer width. Okay, so what I want to do is I want to call this kernel. Oops. I want to call this kernel, okay, oops. Okay, it was called RGB to gray underscore kernel, right? And what I want to do is I want to provide it with the parameters it was expecting. In this case, it's going to be red underscore G, green underscore G, and, oh, sorry, not underscore G, underscore D. Okay, so remember we said that one convention that's commonly used is to use underscore D at the end of the names of the arrays when they point to the device. Okay, and we're going to have blue underscore D, and then the result is going to be in gray underscore D, and then we're going to provide width, and we're going to provide height as parameters. So these are the parameters of the kernel. But what did we say that we also need to give the kernel in order for us in order for us to specify how many threads we want? We need to configure it, right? And the way we configured it is by providing configurations at the beginning inside of these triangle square brackets. So if you remember these configurations that we have at the beginning, okay, what we did is we would give the number of blocks over here. This was called the grid dimension, the number of blocks, and we gave the number of threads per block as the second configuration. So this tells us how many blocks are in the grid, and this tells us how many threads are in each block. Okay, well, this time when we want to configure the grid, we said what we want to do is we want to have a multi-dimensional. So here, the number of blocks in my grid is not just going to be 4. I want to somehow be able to tell it that I want 2 by 2 blocks. Similarly, at my number of threads per block, I don't want to just tell it that I want 16 threads. I want to tell it that I want 4 by 4 threads. Okay? So to do that, I can't just define num threads per block as an integer. By the way, I can name this anything I want. I'm just choosing these names, that you can name these X and Y if you want. Okay, I can't just define this as an integer. I want to somehow define it as a multi-dimensional integer. And there's a built-in type in CUDA that does this, and it's called dim3. Okay, so dim3, what dim3 is that it's an integer that has 3 dimensions, X, Y, and Z. Okay, so when I define num threads per block now, I need to give it 3 dimensions. So what I can do is, let's say I want my thread block to have size to be 32 by 32. What I can do is I can write 32, 32, and in the Z dimension, I'm going to have 1 thread. Z dimension is going to be 1. I don't have a Z dimension. Okay, so by writing this, what I'm saying is I want my thread block to be 32 threads in the X dimension by 32 threads in the Y dimension by 1 thread in the Z dimension. Okay. By the way, if you don't provide a parameter, then the default is 1. So here I actually don't need to provide that 1. If I don't provide anything, then the default is 1. Okay? Now that I have my number of threads per block, I need to define my number of blocks, right? So somebody's asking, what is dim3? So like I said, dim3 is a type that consists of three integers. So it's going to have an x dimension, a y dimension, and a z dimension. Okay, and by writing num threads per block here is going to have x equals 32, y equals 32, and then the third dimension is going to be 1. Okay, so now that I have my number of threads per block, I have a block that's 32 by 32. Now I need to define the dimensions of my grid. Okay, so what are the grid dimensions going to be? In other words, how many blocks am I going to have? Well, the number of blocks is also going to be a multi-dimensional value. Over here, my number of blocks is going to be 2 by 2. How did I get 2? Well, I got 2 because I have a total of 8 threads vertically, and when I chose to have 4 by 4 blocks, then the number of blocks is going to be 8 divided by 4, which is 2. So we're going to do the same thing over here. The number of threads in the x dimension is going to be the width of the image. And what I want to do is I want to divide that by the number of threads per block in the x dimension, which is 32. And the number of threads in the horizontal dimension, in the vertical dimension, is going to be the height. Okay, and I'm also going to divide that by 32. And this gives me the number of blocks in each dimension. Okay. Question?
Yeah. What is the generic way to write this instead of 32? Can we write number of threads per block dot x, for example?
Yes, you're absolutely right, and you're absolutely right. That's what we should do, and I will do that shortly. But that's a very good observation. Thank you for making that. Okay. Before I get to that, there's one thing that I'm missing here. Yes, somebody has a question?
Yeah, can you just repeat? And the first dim3, where did we get 32 and 32?
Oh, I just decided that I wanted to have 32 by 32 thread blocks.
Oh, okay.
Okay, it was an arbitrary decision that I made, but it's not too arbitrary. And next class we'll talk about, you know, what are good values for the grid dimension. But for now, just trust me that 32 by 32 is a good size for the block.
Okay, thank you.
Okay, every block is going to have 1024 threads, 32 by 32, and we're gonna configure the number of blocks is going to be dependent on the dimensions of the image. Someone has another question?
Yeah, in the RGB system, aren't red, green, and blue numbers?
So good observation. So here the reason I called them characters or cars is because R, G, and B are in the RGB system. R, G, and B are 8-bit values, so they're bytes. Okay.
Oh.
So bytes in C can be as unsigned characters. A character is an 8-byte value, and since this goes from 0 to 255, not from -128 to 127, then I made it an unsigned character.
Okay, thanks.
Okay. Well, good observation. Okay, so one thing I need to do, however, is that width may not be divisible by 32, right? So you guys remember, width may not be divisible by 32. So in this case, what do I need to do? I need to somehow take the ceiling, right? Somehow take the ceiling. So to do that, I can do width plus 32 minus 1 over 32, and I can do height plus 32 minus 1 over 32. Some people like to convert width and height to a floating point value, then take the ceiling using the C ceiling function and then convert back to an integer. I prefer just sticking to integer arithmetic. Okay. Now, somebody made a good observation that is there a better way of doing this? Because if I come and change this to 16 by 16 and then change these values, I've introduced a bug in my code. So it's better for me to just stick to using these values over here. And that's a good observation. So what I can do is I can write num threads per block dot x over here, and over here I can write num threads per block dot x. Okay, and then over here for the height, I can use the y component. I can write num threads per block. Oops. I can write num threads per block dot y over here, and then also over here I can write num threads per block dot y. Okay. If you want, if this is very long, you can probably name this something shorter. You can name it whatever you want. I'm just naming it to this long name for clarity. Okay, so now what we've done is we've configured a multi-dimensional grid. So now what's going to happen when we call RGB to gray kernel is that it's going to launch a grid that has these dimensions. It has whatever values we got here as the number of blocks, and then each block is going to have 32 by 32 threads, and all these threads are going to go and they're going to execute the code for this RGB to gray kernel. So now what we still need to do is we need to see how to implement this kernel. Okay. Let's see how to do that. So this is the code that we just wrote for configuring multidimensional grids. As a reminder, I'll always try to have the code that we write for you in the slides so that you can refer to it later on. Okay, so previously we saw that grids have these dimensions, and we said that we have these keywords in order for us to have each thread in the grid distinguish itself from other threads. And previously we just used .x, 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 but as you can probably guess, the grid dimension, the block index, the thread index, and the block dimension also have .y and .z component. Now, in the vector addition example, because these were one-dimensional grids, we don't use those .y and .z component, but in this case, we are going to use them. Let's see what a grid looks like. We said the built-in dimension index variables each have x, y, and z components. So here in this two-dimensional grid that we have, okay, we're going to have the grid dim variable is going to have two components. It's going to have a grid dim.x that refers to the width, the number of blocks in the width, and we're going to have grid dim.y that refers to the number of blocks in the height. Similarly, we're going to have block index.x and block index.y. So here for this thread block over here at the bottom right, its block index.x is going to be 1, and its block index.y is going to be 1. Okay. We're also going to have block dim.x. Okay, we're also going to have block dim.x and block dim.x and block dim.y. So in this case, our block dim.x is 4, and our block dim.y is also 4. By the way, they don't have to be the same. So we could have defined the block dim, we could have had in the thread block maybe 16 threads in the vertical dimension and 64 threads in the horizontal dimension, for example, or 16 by 16. Could be anything. They don't have to be the same. And then finally, for a particular thread, we're going to have a thread index.x and a thread index.y. Okay, so in this case, this thread over here, the thread index.x for it is going to be 2, and the thread index.y for it is going to be 1. So now this thread, if it wants to find its global index, well, the global index itself is going to have two components. There's going to be the global index, there's going to be the row in this image, and there's going to be the column in this image. And it can find its column by doing block index.x times block dim.x plus thread index.x. And it can find its row by doing the block index.y times the grid dim.y plus the thread index.y. Okay, and let's actually go and do that. So when we come to implement our kernel that's going to do the RGB to gray conversion, the first thing that we want to do is we want to have our threads identify, each thread identify which row and which column in the image it's responsible for. Okay, so we're going to write unsigned int row is equal to block index.x times block dim.x. Oops, I should write y over here. The row it corresponds to y, so not x, y. I wrote x out of force of habit, and then plus thread index.y. This is a common mistake, by the way, so be careful from these kinds of bugs. And then we can write unsigned int column is equal to block index.x times block dim.x plus thread index.x. Okay, so now what we've done is every thread has identified the row and the column in the image that it's responsible for, and now every thread knows what pixel it needs to process. Okay, so this is the code we just wrote, and now we still want to convert the pixel. So to convert the pixel, every thread has a row and a column, but you'll notice that these red and green and blue arrays are one-dimensional arrays, right? They're not two-dimensional arrays. Okay, and the reason they're one-dimensional arrays is that in C, when you allocate data dynamically, right, you get a pointer that points to a one-dimensional array. You can't really allocate multi-dimensional arrays dynamically where both dimensions of the arrays are unknown. Okay, so what can we do? What do we do in this case? This brings us to another topic, which is laying out multi-dimensional data. So in C, the convention for storing data is row major order. What do I mean by row major order? What I mean is that if I have an array like this, that consists of two-dimensional data, but I store this two-dimensional data as a one-dimensional array, the convention, this is the logical view of the data, the convention is that when I lay this data out in memory, we lay out the first row, and then the second row, and then the third row, and then the fourth row. So the actual layout of the data in memory is going to look like this. We're going to have the first row, followed by the second row, followed by the third row, followed by the fourth row. Okay. Well, since data is, and this is what what I have done when I've allocated these images. Each of these red, green, and blue arrays is a one-dimensional array where the width and the height of the image, where the pixels of the image are laid out in row major order. So the question is, given that these this array is laid out in this way, how do I take my row and my column and convert that into an index that indexes the one-dimensional array? What do I do?
I multiply the row number by the width of a row, and I add the column number.
Right, exactly. So if you want to look at this as a one-dimensional array, if I want, for example, the pixel in the position 2, 1, okay, then my row here is 2, and my column here is 1. Okay, so the way I find the index into this array, the index to this array is going to be the number of pixels from the beginning. So I'm going to have 4 plus 4 plus 2. Okay, and what that is basically the row times the width plus the column. Okay, the row, which is 2 times the width, so that's 2 times 4, that gives me this rectangle, and then plus the column that gives me the index into the actual row I'm interested in. So the way I find index is index equals row times width plus column. So now that I found my row and my column, what I can do is I can say unsigned int I. So here I is the linear index of my pixel. I can write unsigned int I is equal to row times width plus column. Okay. And now that I've done this, now I can finally, I know what pixel I'm responsible for. So now what's left is to read the red, the green, and the blue components and convert them into a gray component. Okay, so here I can write gray of I is equal to, I notice every pixel is going to have a different row, every thread has a different row and a different column. So every thread will have a different value of I. So every thread is going to be writing to a different output pixel. Okay, so I'm going to write gray of I is equal to red of I. Who knows how to convert from red from
We take their average.
average? Is it just the regular average or is it a weighted average?
I don't know.
Yeah, it's
I
actually
think
weighted
it's
average.
Weighted average.
Is that the
Weighted average 0.25 red, 0.25 blue, and 0.5 green. No?
loosely speaking, there's actually different ways to convert, but you're definitely right that green gets the highest weight because the human eye is more sensitive to green than to other colors. So it's going to be a red times 3/10 plus green of I times 6/10 plus blue of I times 1/10. Okay, so we give 30% red, 60% green, and 10% blue. We don't like blue too much. Okay, there are all kinds of other weights, conversion weights, and they'll all give you images that are slightly different, have slightly different contrast maybe in the image, or it looks slightly different, but then you'll still get the general image. Okay, so this is the RGB to gray conversion code. What are we still missing?
Boundary checks.
Right, the boundary checks, exactly. So this is the code that we just wrote, and we still have the boundary conditions. So maybe my image wasn't a tree, maybe my image was this pretty flower over here. And this pretty flower is not an 8x8 image. This pretty flower happens to be a 6x7 image. So in this case, because of the way threads and blocks work, I'm going to have to launch more threads than I have pixels. And in this case, what I need to do is I need to make sure that only the threads that are writing to output pixels are active during the computation. Okay, so what should be my boundary check in this case? I need to have a boundary check that makes sure that I'm only processing the pixels that are within bounds. Okay, so usually my boundary check checks if something is less than something. So what do I check as being less than what?
Row less than width and
right,
less than
exactly. Right,
something
exactly. This thread over here, the row for this thread is going to be greater than the height. So I need to check that the row is less than the height. And for this thread over here, the column is going to be greater than the width. So I need to check that the column is less than the width. Okay, so I'm going to do if row is less than height and column is less than width. Okay. So this completes my RGB to gray kernel, nice and simple. Okay, and now let's go and see the performance. This, by the way, is the code that we just wrote that includes the boundary check. Okay, so let's go and let's run this code and see the performance improvement that we get. So I'm going to type make. Okay, and then I'm going to type RGB to gray. I have my own machine over here that has a GPU that's dedicated for me. But if you're using the the server that we gave you access to, don't do this because it's not going to work because there's no GPU on the head node. You should use this job submission. So here I write an RGB to gray, and we can see the performance difference. The CPU time takes 3.8 milliseconds. The GPU time takes 1.5 milliseconds, 1.5 milliseconds, so that's more than 2 times faster. And if your image was already on the GPU, so you did not have to incur all this copy time, then the kernel time would just be 0.063 seconds. So that's a significant performance difference. You can do the math and figure out how much faster this is. Okay, maybe I think it's around 50 times faster. All right, exciting, right? Any questions so far?
It's very exciting, but I do have a question, please.
Yes, go ahead.
On C, I've been using 2-dimensional arrays or just an array of pointers, and then each pointer has an array itself. So why? Yeah, sorry about the noise. So why didn't we do that? Thanks.
Okay, so that's an excellent question. So you can do that if you want. You can create the illusion of a two-dimensional array in C by allocating an array of pointers, and then each of those pointers points to its own array. There's two problems with that. First of all, the allocation code in that case is inconvenient because you have to allocate this array of pointers, and then for each pointer you have to allocate an array. So if you have 1,000 by 1,000 image, you're going to have to allocate an array of 1,000 pointers, and then for each of those pointer, call the allocation functions. You're going to have to do 1,000 small allocations. Okay, so one, the allocation is inefficient in this way. The second problem with that is that when you access an array like that, so let me show you my code over here. So over here, when I'm accessing gray of I, okay, I am accessing, I'm performing one load operation. Okay, I get gray, I add I to it, and I load. Whereas if you use an array of pointers and then each pointer points to an array, what you need to do is you need to load the pointer, and then from that pointer load the value. So now if you use the array of pointers approach, every load of your array is actually two load operations as opposed to one load. Whereas this over here is one load operation. Okay. So that's going, and you know, in a lot of computations, memory is your bottleneck. You really don't want to make one load operation two load operations, because that's just going to make you run twice as slow if memory was your bottleneck. Okay, clear?
Yes, but one more question. I don't know, I'm the physics student, so when in C you define a 2D array, not defining an array of pointers and each pointer, but just with the definition, let's say float x, you use two brackets and each bracket has a number in it, which is the dimension. Is that different?
So when you declare a two-dimensional array like that in C, what happens is that you actually get the behavior of this, where you have the C allocates it as a one-dimensional array, and C does row times width plus column for you. But for C to be able to do that, it needs to know what width, the compiler needs to know what width is. And that is why you cannot do dynamic allocation in C with that. If the compiler doesn't know what width is, then the code will not be able to, you will not be able to compile the code. So in our case, we want our both dimensions to be dynamic and not necessarily have to be known at compile time.
Oh, but okay, so that way is more efficient than allocating an array of pointers and then doing that.
Yes, that way is more efficient. However, you're going to face trouble if you want to dynamically allocate, a variable amount of data.
I see. Thanks.
But if for any program you're going to run, that array is always going to have the same size. So maybe it's a small matrix that's always 16 by 16. Then fine, you can use that approach.
Okay, and okay, I guess building on that, just another small question. When you're defining, let's say, block dimensions with the dim3 character or whatever it's called, in the parentheses, can you use a variable?
Yes, of course. Yeah, absolutely. Okay. You can use a variable in here that's passed, from somewhere else. Just like this over here is a variable that's calculated at runtime.
Right. Okay. Thanks.
Okay. Yeah, you're welcome. Thank you for these questions.
Professor, just a small question.
Yes.
In the GPU, is there the equivalent of a heap, a stack, and everything, like a general purpose computer, or no?
Yes, there are these things. They differ from the way they are managed in the CPU, but there are these. There's definitely these notions of a pool where you can dynamically allocate data, and of a stack that runs. And we'll look more definitely at the GPU architecture in the future, so that you guys can get a better appreciation for these things. Okay. Okay, so let's now do a different example. So now let's do image blur. So let's say I had this image and I wanted to blur this image. Okay, so how do we blur an image? Well, one way to blur an image is for the output pixel to be calculated as the average of the corresponding input pixel and the pixels around it. So for example, if I wanted to blur an image, if this was this two-dimensional array was my image, and this was my output image, then this pixel in the output image is going to be the average of this pixel in the input image and the pixels around it. Okay. Now the pixels around it could be, you know, the 9x9 block of pixels. It could be a 16 by 6 or a 25 by 25 block of pixels. I could have weighted average. I could have an unweighted average. There's all kinds of way of blurring things. For today, we're just going to do just a simple unweighted average of the surrounding. Okay. So if I wanted to parallelize this, what's a good way to parallelize it? Any suggestion?
I need to take more than one pixel in one thread. Right.
Okay, more than one
or have
output.
communication between the threads.
Okay, so but are you referring to input pixels or output pixels?
No, the input pixels.
Okay, so you're saying that a thread is going to have more than one input pixel. So
yes.
So what is a thread going to be responsible for?
To take the average of more than one pixel, the square of 9 pixels.
The square of 9 pixels. So we can think of a thread as being responsible for an output pixel, right?
Yes.
Right. So what we can do is we can have a thread for every output pixel, and each thread is responsible for finding the corresponding input pixel and looping over the surrounding pixels and computing the average. Okay. So one parallelization approach is to assign one thread to each output pixel and have it read multiple input pixels. And this is a great approach. Okay. There are better ways of doing this, and we will see better ways of doing this later on in the course. But for the purpose of today, this is a great approach, nice and simple. We have every thread responsible for an output pixel and calculates the average of the surrounding input pixels. Okay, so let's go and implement this. So I'm going to leave my RGB to gray code, and I'm going to go to other code for blur, and I'm going to open my kernel. This time I've already written the launch code that calculates the number of threads, number of blocks, and launches the blur kernel. Okay, and of course all this copy code and copy back code is already written. And what we want to focus on is this blur kernel over here. Okay, so the first step for the threads to find their row and their column value. And we know how to do that. It's going to be the same over here. So this time, so we're going to have unsigned int row is equal to block index dot y times block dim dot y plus index dot y. Okay, and similarly, our column is going to be block index dot dot x times block dim dot x plus thread index dot x. Okay. Now we have every thread has its own unique row and column. Okay. But one thing we need to be careful for is that what row and column are we referring to here? There's two notions of rows and columns here. We have an input row and we have an output row. Okay. So what I'm going to do, just to clarify what I'm talking about here, I'm going to call this out row. Okay, so I have an out row and an out column because later on I'm going to have in row and an in column for these different pixels. Okay, so we have an out row and out column. We need a bound, right? So we need to make sure that this pixel is within bounds. So to do that, I'm going to write if out row is less than height and out column is less than width. Okay, and now that I have this boundary check, now what I can do is I need to loop through my input pixels. Okay. So someone's asking, do I need to check if my input pixels are in bounds? And you're absolutely right. I do need to check that my input pixels are in bounds. But if my output pixel is in bound, at least I know that one of my input pixels is in bounds. The others I may need to check for. So let's we'll take a look at that. Okay, so now what does this thread need to do? Well, it needs to loop over this square over here. Okay. How does it find? It's going to start from up here and loop over. So how does it find where to go? Well, it's going to do the central pixel -1, -1 in the x dimension and -1 in the y dimension to get here. In general, if this it's going to be whatever the radius of my blur is. Okay, so in this case, the radius of my blur is 1 because I'm going to go because the blur goes 1 away from the central pixel. Okay, but my blur could be the radius of my blur could be anything. Okay, so in row is going to start here and it's going to go from here until here. And then in row is going to start here and going to go from here to here, and in column is going to start here and going to go from here to here. Okay, right? For int in row, okay, is equal to what? It's going to be out row minus the blur size. In this case, the blur size is 1, or the blur radius. So it's going to be in row is equal to out row minus 1. Okay, for my blur code to be in general, I have inside of common.h over here, I've defined my blur size to be 1. Okay, this way I can just change this 1 to 5, for example, or to 2, and I'll have a 5 by 5 blur. Okay.
Why is it -1, Professor?
It's -1 because my out row points to here, but I want my in row to start over here. Okay, so I'm going to do in row -1.
Oh, okay.
Okay, and then I'm also going to do, and then in column is going to start at out column -1. Okay, so I'm going to do out row minus blur size. Okay, and then in row is less than, and then here this time it's going the end is going to be out row plus 1. So out row plus the blur size, and then plus 1 because it's not inclusive. So in row is less than out row plus blur size plus 1, okay? Because out row plus blur size, which is index over here, should be included, and that's why we have the plus 1 here, okay? And then we're going to have plus plus in row, okay? And then we're going to have another loop that loops over sorry, I've been pointing to columns the whole time when I mean to point to the rows. I apologize for that. So we're going to start at in row -1, and we're going to go until we get to in row plus 1. And then we're going to have another loop that loops through the columns. So we're going to have for int in call is equal to out call minus blur size. And then in call is less than out call plus blur size plus 1, and then plus plus in call. Okay, and now in this case, what do I need to do? Well, I'm going to need to have some kind of average that I'm accumulating across these different pixels. I want to sum up these pixels, and at the end, I want to divide them by the total number of pixels. So in this case, what I'm going to do is I'm going to initialize an average up here. I'm going to write unsigned int average, and then I'm going to write average plus equals. And now what I need to do is I need to access the corresponding pixel in the input image. So the input image is called image. Okay, and how do I access it? I write in row times width plus in call. Okay, and now that I've looped over these pixels, I calculated the sum. I need to divide the average by the total number of pixels in my square, and then I store that to the output pixel. Here, and for the blurred image, now I need to store the average in this output pixel over here. So for the blurred image, I'm going to write blurred of out row times width plus out call. Okay. And that's going to be equal to the average, okay, divided by the total number of pixels in my in the square over here. So in this case, the total number of pixels is going to be blur size times 2 plus 1. Okay, so here blur size is 1. So it's going to be this blur size plus the blur size in this direction plus 1 for the central row and column. Okay, and then it's going to be that times itself. So I'm going to, the average is going to be divided by 2 times blur size plus 1, okay, times 2 times blur size plus 1. Okay, so in this case, blur size is 1, so 2 times 1 plus 1 is 3. So I have 3 times 3, and I'm going to divide this average by 3 times 3, which is 9. Okay, and then finally, I'm going to take this whole result and I'm going to cast it back to a character so that I can store it in the final image. Notice that I declare this as an int and not a character, because when I'm calculating the average, I need to get the sum first, and the sum might be larger than 255. So that's why I sum it up as an int, and then I divide it and then convert it back to a character. Okay. Someone asked me to initialize to 0. I absolutely do need to initialize to 0. So thank you for that reminder. Okay, any questions? Is this code clear to everyone? Okay, so let's run this. Let's compile it. And now let's run this and see the performance that we get. Oh, wait. Actually, there's something wrong here. I just realized that we have a mismatch. So maybe this was not a correct result. Let's see what the problem is. So I got a little excited and I ran the code early. So this is the code that we just wrote, but the punchline was that when we ran it, we had a mistake, okay, and we were supposed to keep going and try and figure out what the mistake was. And the mistake was that we're not handling the boundary correctly. So the boundary condition, for the boundary conditions, this pixel over here, all the inputs are in bounds, but we could be in a situation where the input is not in some inputs are not in bounds. So for this pixel over here in the corner, these inputs are in bounds, but the other inputs are not in bounds. Similarly, for these pixels here at the edge, we have some inputs are in bounds, but the others are not in bounds. So what do we need to do? Well, we need to handle the boundary conditions. So even if the output pixel was in bounds, the input pixel may not be in bounds. Okay? So what do we need to do? We need to check if the input pixel is in bounds before adding it, which is something that I forgot to do because I was excited to run the code for you and show you the speed up. But you know, when you're writing your own code, you should always make sure that you don't get too excited and always look at your boundary conditions before racing to find out the speed up that you got. Okay. Take a look at the boundary conditions. So this is where we are accessing pixels. So basically what we need to do is we need to simply check that this access to the input image is within bounds. And to do that, what we can do is we want to check that in row is within bounds and in column is within bounds. Okay, so here we'll check that in row should be less than, well, in row, first of all, in row should be less than height. Okay, but also another important thing is that if out row was 0, in row could be negative. Okay, and this is actually why I used int over here and not unsigned int, because in row could have a negative value. And in this case, we also need to check that in row is greater than or equal to 0. Okay, same thing for the column. We need to check that in column is greater than or equal to 0, and we need to check that in column is less than height. Okay, and after we do that, now hopefully our code will compile and it will run.
You have to count the pixels also when you want to divide the average.
Well, it depends. It depends on how you define your blur. It just depends how you define your blur. You can define it to where you have to count the pixels, or you can define it to where the pixels on the boundary are just a little bit darker.
Oh.
Okay. So in this case, for simplicity, I'm not doing that. But you're right that in some cases you might just you will also count the pixels that you're summing up and use that as the denominator.
Professor, مش
Yes?
مش incol لازم تكون less than width مش height.
Yeah, that was my mistake. See, this is the thing. I like to write and run code with you guys in class because I feel like it makes things more accessible. But that's always when you do that, you always risk making these silly mistakes as you are rushing, and that costs us some time sometimes. We're still not getting the result. Okay, let's move on and I'll take a look at this later and see where we went wrong. Okay. Okay, so the bug that was in the slides is that over here, out of habit, I had used unsigned int for outro and out column. Okay, however, these should not be unsigned ints. They should be regular ints. Okay, and the reason is that over here, when I was doing a subtraction on unsigned int, this results in some weird behavior that that's undesirable. So hopefully this should solve the problem. So let's now try recompiling, okay, and running. And now this time we don't have a mismatch. The result passes. Okay. So here you'll notice that for the timing is similar to the timing that we got before because these were just little bugs, but did not really affect the timing. Okay. So now we got to the bottom of what kinds of bugs can happen when you are writing this parallel code. And I think it's good that we experienced these kind of bugs in class because you guys get an idea of what are the typical kinds of mistakes that people do when they're doing parallel programming, and hopefully this helps you avoid these kinds of bugs when you're writing your own code. Okay, so this is the code that we just wrote, and a rule of thumb for boundary conditions is that our boundary condition, the rule is that every memory access must have a corresponding guard that compares its index to the array dimensions. Okay, one of the hardest things to get right, I often say this, I say half of parallel programming is index computations and boundary conditions. Okay, half of parallel programming is index computations and boundary conditions. And one of the key things one of the rules of thumb for boundary conditions is every time you have a memory access, you should have a corresponding guard that checks if the index of that access is in bounds. Okay, so here we have a memory access over here to the image. Then in this case, we should have a corresponding guard, which is this one over here, checks that that access is within bounds. Here we have a write to the blurred image. Then we should have a corresponding access that checks that that write is within bounds. Okay. So this is just something to keep in mind. Whenever you write code, if you want to make sure that your boundary checks are correct, always look at every memory access and trace it to a corresponding check on the bounds. Okay. All right, let's do our final example. Matrix multiplication, the computation that everybody loves. So matrix multiplication consists of multiplying a matrix A by a matrix B to get some matrix C. Okay, and how do I multiply two matrices? Well, the matrix C, in the matrix C, that's the output matrix. Every element in the matrix C is going to correspond to the dot product of the corresponding row in A and the corresponding column in B. Okay? If I multiply a matrix A with a matrix B to get a matrix C, for every output element in the matrix C, I'm going to do a dot product of the corresponding row in A with the column in B. Now, question. So when I do this, okay, what is a good, if I'm gonna do this sequentially, I just loop over the output pixels and I can just do a dot product for each pixel. If I do this in parallel, what's a good way of parallelizing this?
A three-dimensional matrix, maybe?
Doing it column by column.
Okay, so three-dimensional matrix, some people said three-dimensional matrix, some people said column by column. Can you explain? So what do you mean column by column?
For example, every column of C is the first column of A times matrix B.
Okay, so you want to assign a thread to every column in C.
Yeah.
That's one way to do it. Can we extract even more parallelism than that?
Well, each thread can be the cell output matrix.
Right, exactly. So that's one straightforward way of extracting even more parallelism, is we can assign a thread to every output element of C. Okay, so one parallelization approach to assign a thread, one thread to each element in the output matrix of C. So this output matrix can be divided into blocks, and every block is going to be a two-dimensional array of threads, and every thread will be responsible for one output element in C. Okay. Okay, so let's go and take a look at. Let's go and implement this. So I'm gonna clear this. I'm gonna go to my matrix code. So over here, I've already implemented the code that does the copying and the grid allocation and everything. Okay, so what I still need to do is I need to implement the kernel. So like I did before, I'm gonna determine the row and the column. So I'm gonna write unsigned. Row is going to be equal to, you should have this memorized by now, block index dot y times block dim dot y plus thread index dot y, and then we're going to have unsigned column is equal to block index dot x times block dim dot x plus thread index dot x. Okay, and then I'm going to do float sum is equal to 0.0f. So I initialize the sum to 0 and then do the dot product. So I'm going to go through this row and this column, and I'm going to accumulate the product. So I'm going to do for unsigned and I is equal to 0, I is less than n. So here n is the dimensions of the matrix. Each one of these matrices is n by n. Okay, and then plus I. To do sum plus equals, and then I'm going to load the corresponding element in A and multiply it by the corresponding element in B. So when I is 2, for example, I'm going to do row times n plus 2, or in general, I'm going to do row times n plus column. Okay, so here I'm going to write A of row times n plus column. Okay, I'm going to multiply that with the corresponding element in B. So here, if I is 2, then I'm going to do, or if I is 2, then I'm going to do 2 times n plus the column. Okay. So here I did row time, when I was 2, I did row times n plus 2. Here I did 2 times n plus column. So in general, I would do B of I times n plus column. Okay, and then finally I need to write out the result. So to index C, I'm going to do row times n plus column. So I'll write C of row times n plus column is equal to sum. Okay. So let's run this and see how well it performs. I'm going to compile it. Okay, and then I'm going to run my matrix multiplication. And oh, okay. So this should have been row times n plus I. Okay, so this should be row, which is the row of the output element, times n, which is the number of elements in the width, plus I, because I is the index that's iterating through these. Okay, so I think I said I, but I wrote column accidentally, or maybe I said column accidentally. I apologize for that. So this is I, and then I'm going to compile that again, and this time I'm going to run it, and this time it succeeds, and you will see that here the CPU time is 200 milliseconds. The GPU time with the copy time is in the order of 4 milliseconds. So we have almost 50 times speed up, and then if you exclude the copy time, you have 2 seconds, which is around 100 times faster if your data is already on the GPU. Even if you have to copy your data, it's still worth it here because you're going 50 times faster. Okay. And there's a reason why matrix, and by the way, we're going to see techniques throughout the course where we're going to go even faster than this. And there's a reason why matrix multiplication in particular performs so well compared to image RGB to gray conversion, for example. All right, any questions?
Yes, Professor. So the way I've been thinking about this, I'm not sure if it's right. So for example, the matrix multiplication needs normally three for loops.
Okay.
So basically, if you have 3 for loops, does that mean that you would need 3D blocks or no?
No, not necessarily. But if you want to think about it in terms of loops, once you're familiar with parallel, once you get used to parallel programming, you stop thinking in terms of loops. But if you want to think of it in terms of loops, you can think of your row index corresponding to one of the loops, and your column index corresponding to one of the loops, and then you have this for loop that's in your code. That's the third loop. Okay.
Okay, I see. Thank you.
With the other examples, with the RGB to gray conversion, okay, you don't have an inner loop. So you have 2 loops in RGB to gray conversion. The loop over the output element in the sequential code. So here the first index corresponds to the first loop, and the second index corresponds to the second loop. Okay, so you can think of this as almost you're parallelizing your loop, where every thread is taking one of those loop iterations.
But
okay?
that's why I was saying, so with matrices, since you have 3 loops, why include the third one inside? Just parallelize it too.
I see what you mean. So what you're suggesting is that why don't we parallel this loop over here as well? And the answer is you can parallelize it. This is a little bit harder to parallelize, and the reason is that you have a loop carried dependency here because you're doing an addition across this loop. Right? So that loops through this, there's a loop carried dependence because you're doing an addition across it. Whereas the loops that loop over your output, every iteration is completely independent and doesn't depend on the others. So this one would be a little bit more difficult to parallelize, and whether or not it's worth parallelizing depends on your input and depends on all kinds of things. Okay. So we'll look at these kinds of considerations later on, of course. But whether it's a good idea to parallelize this loop is another story. But whether it is possible, the answer is yes. You could declare a 3-dimensional grid and parallelize this loop in the 3rd dimension. That's a completely possible alternative. Okay, so some final things to take note of. So this is the code that we wrote. One thing to take note of is boundary conditions. So here your output may not be evenly divisible by your number of blocks. So you should take, this is something that we would need to take note of here in this code. We would need to somehow place a guard to make sure that our output is that our output is that we don't write anywhere that's out of bounds. And then another thing to take note of is that we could have a case where we have different matrix dimensions. So I've used a square matrix in this. All my matrices were n by n in the lecture. But you could have matrix multiplication for matrices that are, A could be m by k, B could be k by n, and then in this case your output would be m by n. So my matrix dimensions could be different from each other. And you will have an assignment that will be released soon, where you will have to implement matrix multiplication, but you will have to do it for the more general case of having an m by k matrix multiplied by k by n matrix to get an m by n matrix, and you will also have to deal with the boundary conditions in that assignment. So I will leave handling these boundary conditions for matrices with different dimensions as an exercise for you guys to do in the upcoming assignment. Okay. The material we covered today corresponds to chapter 3 and these chapters and sections of the textbook. So feel free to read in the textbook if you'd like to read more about what we covered today. And that is all for today. And I will see you next time.